You know, for decades, we've looked up at that little red dot in our night sky and dreamed of putting boots on its rusty ground. But not just a visit, right? We're talking about staying, building a second home for humanity out there among the stars. So the big question is, how do we actually turn that amazing science fiction dream into an engineering reality? Well, let's explore the blueprint. This right here, this is the goal. A bustling, self-sustaining industrial outpost on Mars. You've got habitats, rovers, power plants, all working together. But getting from our world to this one and making it truly independent, well, that is one of the greatest technical challenges humanity has ever faced. I mean, think about it. You can't just pack up a city and ship it 140 million miles. The cost, the complexity, it's literally astronomical. So if you can't bring it all with you, you've got to build it there. But with what? And that right there is the huge question we're digging into today. Okay, so the first and most fundamental problem is weight. Every single kilogram when launched from Earth costs an absolute fortune. To build an entire industrial base, you'd have to launch an impossible amount of stuff. So the only way forward is to forget about the cosmic moving truck and learn to live off the Martian land. This brings us to the core concept, the real key that unlocks Mars. It's called in situ resource utilization, or ISRU for short. And it's a pretty simple idea with truly profound implications. You use what's already there. You turn the Martian dust, the ice, and the very air itself into everything you need to survive, and eventually to thrive. And luckily for us, Mars provides the essentials. Its atmosphere is over 95% carbon dioxide. And we know for a fact from multiple missions that there are vast deposits of water ice frozen just beneath the surface. Now, with just CO2 and H2O, you've got carbon, oxygen, and hydrogen. And those are the foundational building blocks for water, for breathable air, for rocket fuel, and even for plastics. Okay, but to turn all those raw ingredients into useful products, you're going to need a ton of energy. So before you can build a single habitat or manufacture a single tool, you have to solve the first and most critical hurdle of all. How are you going to power your Martian colony? And this brings us right to the great power debate. On one side, you have nuclear fission. We're talking compact reactors that offer constant, reliable 24/7 power day and night, even through massive dust storms. On the other side, you've got solar, photovoltaics that have become incredibly lightweight and efficient, but they only work when the sun is shining. So which one do you pack? Well, this chart here makes a really compelling case for nuclear. This was an analysis of what it would take to run a really power-hungry propellant plant. NASA researchers calculated the total mass you'd need on Mars. The blue bar is the plant itself, and that orange bar is the power system. And as you can clearly see, the Fission Surface Power System, the FSP, results in the lowest total mass. It's actually lighter to launch than even a big solar farm right at the equator. But wait, here's the counterpoint. A pretty recent study from UC Berkeley argues that when you're not just running one specific factory, but powering a whole settlement, the game completely changes. Thanks to some new, highly efficient and super flexible solar panel tech, solar actually beats nuclear when it comes to launch weight for nearly half the planet's surface, especially around that equatorial band. So the really crucial thing to understand here is that there's no single right answer. It's all about a series of trade-offs. Nuclear gives you unmatched reliability, which is a huge advantage when a planet-circling dust storm can block out the sun for weeks at a time. But modern solar panels are so lightweight they can dramatically cut down the mass you have to ship all the way from Earth. The best choice? It really depends on your mission. Where are you landing? And what exactly are you trying to do once you get there? Okay, so you've picked your power source, you've got the lights on, what's next? Well, you need a place to live. You need a shelter that can protect you from Mars's absolutely brutal environment. We're talking freezing temperatures, a super thin atmosphere, and a constant bombardment of cosmic radiation. One of the most compelling ideas out there is to just go underground. This concept uses swarms of robots to do all the heavy lifting. They dig down into the Martian soil and then use that excavated material, the regolith, to create a kind of Martian concrete. That concrete is then 3D printed or sprayed to line the tunnels and make them stable. And then, finally, inflatable habitats are placed inside, creating a safe, pressurized living space that's shielded by meters of natural Martian rock. And this just illustrates the concept brilliantly. On the left, you see this whole network of underground spaces, all connected by tunnels, all safely below the surface. Then on the right, you see the robotic 3D printing in action, creating this complex, structurally optimized shell that's both incredibly strong and really efficient with its material. I mean, this is high-tech construction for a whole new world. But, living in a cave might not be for everyone. What about surface habitats? What about a room with a view? Well, the problem, in one word, is radiation. Mars doesn't have a thick atmosphere or a global magnetic field to protect it, so the surface gets blasted with dangerous galactic cosmic rays. Any structure on the surface needs some serious shielding. Now, this table shows just how critical that shielding is. Researchers modeled a habitat shielded by layers of a type of plastic called high-density polyethylene, mixed with Martian regolith. So out in the open, the daily radiation dose is about 0.28 millisieverts. But look what happens. Just look. When you place that same habitat in a spot with protective terrain, like next to a cliff or in a small crater, the dose just plummets to 0.06. That's an incredible difference. It just proves that smart site selection is every bit as important as the shield itself. All right, now let's see how this all starts to build on itself. Once you've got power and shelter, you need to start making things. And this is where ISRU goes from simple survival to building a true industrial ecosystem, a whole web of processes that turn Martian resources into the critical supplies that make a settlement truly permanent. So, take a look at this. I know it might look like a crazy mess of pipes and boxes, but what you're seeing is a diagram of a Martian chemical plant. Water from a subsurface mine and CO2 from the atmosphere go in one end, and after a series of chemical reactions, what comes out the other end is liquid oxygen and liquid methane. In other words, this machine turns Martian air and ice into the rocket fuel you need to get astronauts back home. It's incredible. And it doesn't just stop at fuel. This flowchart shows another amazing process. Again, you start with just water and air, and you can create ethylene gas. Then, through a process called catalytic polymerization, you can turn that ethylene into polyethylene, or HDP. Yep, the same plastic we saw earlier in the radiation shield. This stuff can then be injection molded to create those shielding modules, or spare parts, tools, pretty much anything you can imagine. This is a self-sufficient spare parts economy in the making. So the crucial takeaway here is that building a life on Mars isn't about finding one single silver bullet technology. It's about creating an integrated industrial roadmap. A nuclear reactor might make total sense for a fuel plant way up in the high latitudes, while a settlement near the equator could thrive on lightweight solar panels. An underground habitat gives you the best radiation protection, but a modular surface habitat might be way more flexible. It's all a complex, interconnected system, where every single choice affects every other choice. In the end, Mars is the ultimate fixer-upper. It's got good bones, as they say, but it needs a lot of work. And the really amazing thing is that the blueprints for how to actually do that work, they're being drawn up right now, in labs and research papers all around the world. We are literally figuring out how to build a world. And that leaves us with one final, fascinating question to think about. As we write this incredible new chapter for humanity, what kind of story do we want it to tell?